will now discuss volumes using a method known as slicing. So the idea is we have this strange shape that we want to take the volume of. So we're going to look at the area of individual slices. So our general method is if a solid object extends from x equal to a to x equal to b, and we have a cross-section of the solid perpendicular to the x-axis, has an area given by a function a that we can integrate, the volume of this solid is given by the integral of the area. So for example, let's consider a solid that has a unit circle as its base, and its cross-sections, taken perpendicular to the base and to the x-axis, are squares. We want to find the volume. So we need to start with our area function. Well, our cross-sections are squares, and so we know how to do a squares. It's the side squared. So what is the side? Well, that depends on where it is on the circle. So we have this circle that's our base, and we have these squares coming off of it. So I'm going to have to solve this equation for y to determine the length of the base. So I have x squared plus y squared equal to 1. This means y squared is equal to 1 minus x squared. So y will be equal to the square root of 1 minus x squared. So that's what y is. In reality, if I look at my axes, y would just be half of this circle. It's not the entire circle. So I would need to multiply this by 2. So I have 2 square root of 1 minus x squared, and that's the length of one side. So we would square this. So now we would need to integrate. This extends from negative 1 to 1. And if we simplify this, we get 4 times 1 minus x squared dx. So this is the integral from minus 1 to 1 of 4 minus 4x squared dx. The integral of 4 is 4x. And then the integral of 4x squared, we would increase the exponent by 1 and then divide by that number. Then we need to take this between 1 and negative 1. So I have 4 times 1 minus 4 over 3 times 1 cubed minus 4 times negative 1 minus 4 over 3 times negative 1 cubed. So this is 4 minus 4 over 3 plus 4 minus 4 over 3. And this gives us 16 over 3. So a solid of revolution is a specific type of solid that we're going to be looking at. So if we have this continuous function that's positive on the interval from a to b, and we let R be the region bounded by the graph of f, the x-axis, in the lines x equal to a and x equal to b. Then we will revolve R around our x-axis, and as it revolves once, it gives us a three-dimensional solid of revolution. And so our goal is to find the volume of this solid. And if I think about what's happening, I'm taking a single point and wrapping it around our x-axis. So my individual slices are going to look like circles. So here's an example. I have this graph that I'm going to be rotating about the x-axis, and I can see that at every point it's going to give me this circle. And we know how to find the area of a circle. It's pi r squared. Well, in this case, r will be the distance from f to the point y on the graph, which is by definition f of x. So pi f of x squared. So like I was saying, if we have this continuous function that's positive on the interval from a to b, we let r be the region bounded by this graph, the x-axis, and the lines x equal to a and x equal to b, and we revolve it around the x-axis. Our volume is given by the integral from a to b of pi f of x squared.